rested up and ready to go because it's 8.3 time geometric sequences in series. So we're no longer looking at arithmetic sequences in series. We're looking at one that's called geometric. Okay? And what we're hoping to do today is recognize and be able to write geometric sequences, find the nth partial sum geometric sequences, and find the sums of infinite geometric sequences. So let's get started. What classifies a geometric sequence? Well, we saw in arithmetic sequences that they had to have what's called a common difference. Right? It was when you took the two terms right next to each other, subtracted them, they would have the same common difference. Same type of idea for geometric sequence, only this time what you're going to do is divide the two terms, the consecutive terms, and we're going to find what's called a common ratio. So I take, say, the first term and the second term, divide them, and I would get some common ratio that would be equal to if I took the third and second terms and divided them, or the fourth and third terms and divided them. And this particular ratio just can't be a 0 in order for us to have this geometric sequence. So once we have that R value, that common ratio, we're good to go. So let's check this out. If I have something that says 2 to the n, is that a geometric sequence? Well, let's start taking a look at some of those terms. If I have 2 to the first, that's 2. 2 to the second would be my next term, so that would be a 4. 2 to the third would be my next term, that would be an 8. And then it would be a 16. So, do I get a common ratio? Well, 4 divided by 2, is that equal to something like 8 divided by 4? Is that equal to something like 16 divided by 8? Right? I'm taking the second term, dividing it by the first, taking the third term, dividing it by the second, or the fourth term divided by the third. Are all of these things equivalent? As a matter of fact, they are. They all have the same common ratio, which in this case, R would be a 2. 4 over 2, 8 over 4, 16 over 8. Now let's check B. Does B have a common ratio? Well, let's check it out. We got 4 times 3 to the n, so my first term would be 3 to the first, which is just 3. 3 times 4, 12. My next one would be 3 squared times 4. 3 squared is going to be 9. 9 times 4, 36. My next one would be 3 to the third, which is 27. 27 times 4. And then my next term, we'll go up one more. It's going to end up being 324 when I do 3 to the fourth times 4. Alrighty, let's check this out. 36 over 12. Is that the same thing as 108 over 36? Is that the same thing as 324 over 108? Well, let's check it out. This is 12 goes into 36 3 times. 36 goes into 108 3 times. 108 goes into 324 3 times. They all have a common ratio of 3, R. Fantastic. That also is a geometric sequence. Alrighty. Now, just like there was a particular format for arithmetic sequences, there is a particular form for geometric sequences. So my sequence will equal the first term times that ratio value, that R, which will then be raised to the exponent of n minus 1. Ready? So, what we in essence get here is the first term being a sub 1, the next term is a sub 1 times the rate, the next term is a sub 1 times that rate or ratio squared, the next term a sub 1 times that ratio cubed, and it just continues to move up in what appears to be a sort of geometric type situation, or an exponential type situation. So if you think of like an exponential function, these are very closely related. Now let's look at how we find the sum. Alright, I already know that this is how my geometric sequence is going to look. I also already know that this right here is how I represent a geometric sequence as an expression. Right? The first term times the rate raised to variable minus 1. So the summation is simply saying I'm going to use I, and I is going to go from 1 all the way to a certain number, however many partial sums we want to do. And the formula that we have for computing this for geometric looks like this. The first term times this fraction with 1 minus r to the n on top and just 1 minus r on the bottom. So it should be pretty simple to do. So what I want to do first is find the following sum. So I'm using an n for my variable, and I want to start at 1, and I want to go all the way to 12. Now I could take 1, put it into the equation, find the first term, go and put a 2, and put a 3, and a 4, and a 5, and a 6, all the way up to 12. But it's probably going to be pretty time consuming. So why don't I just find the first term? And I'll use my formula. My formula tells me that I want a sub 1 times 1 minus r to the n on the top, 1 minus r on the bottom. And that's going to help me find the partial sum, particularly in this case, the 12th partial sum. That's my n value. So my first term, that's the first thing I need to do. When I put a 1 into this equation, it's just 4 times 0.3. So that's my first term, 4 times 0.3. And then that needs to multiply 1 minus r. Now, if I look at the original format for this type of equation, it's the first term times r raised to the exponent. So in here, it's the first term times r. So my r value is 0.3 raised to the n. My n value in this case, is a 12. And then on the bottom here, 1 minus my r value, 0.3. So, when I evaluate, I got 1 minus 0.3 raised to the 12, 1 minus 0.3, and 4 times 0.3. All of this together comes out to 1.71. And that would be my summation for the first 12 terms of this particular sequence. Simple enough, just using a formula. Now, there's something very interesting that happens with this formula right here, when certain conditions are held. Conditions that have to do with the rate itself. Now, the rate is being raised to an exponent here, r to the n. As that n value increases, and we assume that we're getting closer and closer and closer to finding an infinite series, so the n value is going farther and farther to infinity, just like we say right here. When that happens, as long as the r value is a number that's non-negative but less than 1, so meaning it's a positive fractional value less than 1, that fraction, when being raised to a larger and larger and larger power, becomes closer and closer and closer to a 0. Right? So this thing becomes closer and closer and closer to a 0 as we get closer to having a infinite series. When that happens, the only thing that's left in my numerator is a 1, which means that I can simplify this entire equation for an infinite series to look just like this, where the a sub 1 multiplied the 1 in the numerator and the 1 minus r in the denominator just stayed the same. So this is what we're going to use for when we're trying to find an infinite series. So, for example, I have a different equation here, very closely related to the last one. I'm starting at n equals 0, going all the way to infinity, and I want to try and find what my value is that I'm approaching. So, here's what I'm going to do. I'm going to go and I'm going to use my formula, which tells me that I should be able to do a sub 1 over 1 minus r, simply because this is the summation of an infinite series. And there we go. A sub 1 times r raised to the n minus 1. Cool. So let's just plug some values into here. Alrighty. Let's see. A sub 1 is simply going to be the first term of the expression. So that's going to be when I take my value right here in my expression, the 4. There it is. And then what I do is I put that over 1 minus the rate. The rate here is going to be a 0.6. And when I evaluate, what am I going to get? 4 divided by 1 minus 0.6 is basically 4 being divided by 0.4, which means 10. 10 is the solution to the infinite summation there, which means this geometric sequence is going up to and approaching 10 as we move closer to higher and higher values of n reaching infinity. Now part B. Part B, we're not explicitly given the equation, so we have to kind of go ahead and use certain parts of it a bit differently. I am still going to do the same idea because I'm trying to find the infinite sum, where I take the first term and I subtract it by 1 minus the rate. So really I just need to try and figure out what that rate is. And in this case, if I take 0.3 divided by 3, making that the same as 0.03 divided by 0.3, the rate that it looks like I'm coming out with is just 0.1. Really, every time it's a tenth of what it was before. So I'm going to take the first term, 3, and I'm going to put it over 1 minus that tenth. And what am I going to get there? If I do 3 divided by 1 minus a tenth, so 3 divided by 0.9, it's going to be basically 3.33. And that's what I'm getting for my summation of the infinite series that looks like this. Alright, so hopefully that's not too crazy. It looks like that's the end of this one for us. So we went over a couple of different things. Using the formula can be a little bit confusing sometimes when we're looking at taking that first term, the a sub 1, especially when we're dealing with infinite series sometimes. But hopefully everything will be good. Write down questions if you have them. Obviously we'll go over them when we do all of our examples in class. And I will talk to you all later.